Welcome to today's lecture on autonomous driving stacks. My name is Daniel, and together with Markus, we would like to give you a motivation how and why to use autonomous driving stacks. We would like to give you an introduction to the architecture of such a stack based on Autoware. We will briefly discuss different autonomous driving stacks that are around. We would like to show you how to integrate Autoware into a real vehicle based on a Ford Fusion platform. And finally, we would like to give you a couple of other use cases using Autoware. Let's start with our first part in our lecture, which is the motivation to use autonomous driving stacks. Within this part, I actually would like to give you an overview. What is the autonomous stack? What is the full stack, the full mobility stack? I would like to introduce the high-level architecture of autonomous vehicles. What about the signal flow within this architecture? What are the building blocks of autonomous vehicles? And would also like to focus a bit more on the control layer, what timings are required there, what is the difference between safety critical, mission critical, low critical and mixed critical systems. Before we actually focus on the Autoware software stack, we have to understand the full stack, which is also called the autonomous mobility stack. That one consists of several layers. If we just look at the first part, that's the hardware stack, that consists on the highest level of the vehicle, the components and the sensors. You see always a couple of examples, like on the sensor level we have GNSS, we have the INS and IMU, Lidar sensors, camera, radar sensors and all other sensors which are belonging to this layer of sensors. So that's just the hardware stack. The next part actually is the off-board software and data part, which is also part of the full mobility stack. So we have a lot of parts in there, and it's quite important to understand that a stack is not only the hardware or the software, it's actually much more than that. It's the entire environment. It means all the tools, the processes, the methods, the algorithms that are used to run this mobility stack. So if we look right on the off-board software, we have maps, how to do or how to create the maps. What about, let's say, the operations like fleet management, fleet routing, teleoperation, diagnostics, over-the-air, update services. We have the entire data processing, which also includes the data recording, which is pretty much important for driving on public roads. It's mandatory to have a data recorder, a black box in your vehicle, for instance. Then, as I said before, all the development tools are part of the off-board software and data stack as well. Then all the methods and methodologies that are required for the design, for the testing, and of course the functional safety and the functional security. That also includes all parts of verification and validation. As you can see here, we have the basic unit tests, we have also integration tests, we have software in the loop, hardware in the loop, vehicle in the loop, the proving ground tests, and also of course the public road testing. Then finally, of course, we have the onboard software, so the actually part where most of us are interested in, which is the operating system, the real-time system, which is the framework software, including the middleware, safety support, security support, again the diagnostics part, and the algorithms. So all those fancy things like perception, tracking, sensor fusion, machine learning based methods, how to localize, for instance, Lidar based localization, how to do the route planning, trajectory planning, decision making under uncertainty, the motion planning, the path matching. It's all there in the onboard software and the software stack. And finally, we have, of course, a product. The autonomous mobility stack finally is a product that has to be integrated in the real platform with a certain application, and finally has to be released. So that's basically the autonomous mobility stack from again consisting of the hardware stack, the off-board software, the methodologies, the on-board software, and the final product. If we now focus a little bit more on the high-level architecture of such an AV, we actually have to understand that our final product has to deal with a lot of unpredictable conditions. That could be bad weather conditions, that could be roadworks, that could be suddenly occurring objects, like here a kid running with its ball. So many complex situations that can happen. We have a lot of sensors, radars, lidars, cameras, infrared sensors, ultrasonic sensors, wireless sensors, and other sensors like rain sensors or vehicle speed sensors that can be used. And given the different sources and all of those sensors, they have benefits, they have disadvantages, can be used to come up with, let's say, a fused environmental model. And that, of course, has to be delivered in real time. And sensor data fusion or multi-sensor perception itself is a very complex topic with a lot of people around the world working on that. Given that we have the environmental model, we actually can proceed with the planning part, which is actually understanding the scene, decision-making under uncertainty, the planning part, and for SAE level 3, we still have to consider that the driver could take over. That means driver monitoring is in there. And of course, for level 4 and level 5, driver monitoring could also make sense just to check if all passengers are in a healthy state. And the last layer, sense, plan, act, is the act layer. That means we need the X-by-wire actuation, the low-level control, so that we can follow a predefined trajectory or a predicted trajectory. So that's the main building blocks of an autonomous vehicle. Of course, we have to make sure that all hardware blocks behind and all software blocks, all algorithms are working properly 24/7. And that's why we actually need something like a monitoring system, something that just checks the reliability of the overall system, that monitors the performance, hardware and software issues all the time. And of course, also the driver has to be checked. For instance, is the driver out of position? Usually you can generate warnings, and that of course can be changed to interventions. So that's one of the very important topics that we have, this fourth block, which is the performance and driver monitoring. If we now look a bit closer, how is the signal flow within the different blocks, sensors, the perception layer, the planning layer, and the control layer. We can see here, based on a nice graph from Udacity, how different sensors are interacting with certain functions and influencing the planning layer. Just have a look at the camera. The camera actually, so the signals from the camera are used for lane detection, for the traffic light detection and classification, for the traffic sign detection and classification, and for the object detection and the tracking. So the camera gives the input to those four functions. And if we just consider now the lane detection actually influences the planning layer. It influences the prediction of the trajectory, so what happens over the next couple of milliseconds and seconds. It of course influences the behavior planning and the trajectory planning. And as you can see here, if you look at the behavior planning itself, we also need, of course, the localization. That means whatever kind of localization we are using, GPS-based or LiDAR-based, that's again influencing the behavior planning. The control part, which is just a gray box right now, is the next part. We would like to have a closer look in there. If we proceed, and it's just a different way of showing the architecture, the overall architecture of an autonomous vehicle, with the environment to the left, the vehicle the bottom, and the driver to the right, especially for SAE level 3 functionality. For level 4 and level 5, the driver is not that important anymore and becomes a passenger. If you now look at the planning part, we see that there are 3 different levels in there: the strategic level, the tactical level, and the reactive level. So that means the planning or control layer consists of 3 different blocks. The strategic level is on a navigation level, the tactical level is on a scenario level, and the reactive level is an obstacle, avoidance and stabilization level. And as you could imagine, those 3 levels in our hierarchical control layer work on different time scales. And that's the next part I would like to introduce. If we see to the, let's say, the 3 blocks from the top to the bottom, we have again the 3 layers of the control block, starting with the strategic or mission level. That's actually 10 plus seconds, so a very, very long time period. It's the highest level task for planning a trip. It's just using the navigation system. I would like to go from A to B. It's the route planning and the compliance to riding laws. The tactical level is even shorter, so from, let's say, seconds to up to 10 seconds. It's the vehicle in the traffic. So you still have enough time, up to 10 seconds, for doing or for following your control laws, for instance, lane following, merging, object and event response execution. So you still have a lot of time there. Of course, that depends on the vehicle speed. It's different in urban scenarios and on the highway. And the very short level, in terms of time, is the reactive level or operational level. Here we have to react in milliseconds, up to 100 milliseconds. That actually means split-second reactions and adjustments to lateral and longitudinal control. So that could actually happen if someone jumps into the street or something unforeseen happens. And of course, you have to react in a very, very fast manner. So we have different time layers for those 3 control blocks. And I also put the active safety layer there because the active safety layer is very important. It's always in parallel and has to be ensured. It's meanwhile, so many active safety functions are mandatory, both in the US NCAP and the Euro NCAP, also in the Asian version. That actually means the reaction to a threat. And we have functions like automated emergency braking, which are already released, and you actually can buy those kind of functionalities. Here we have a very huge range from 100 milliseconds up to 15 seconds, where we have to consider active safety systems. If you now actually summarize the different levels in our autonomous driving stack, we actually have to introduce a few terms. The first one is the safety critical part, or the safety critical element. That actually means safety critical systems is the highest and most important criticality level. That means we have to fulfill hard real-time there. So that one is imposing very hard constraints to our software development, to our software stack, to our function development, to our algorithms, and to our hardware platforms, because we have to respond in real time. That's, so just go back, relevant for the reactive layer and also for active safety systems. Then we have the next criticality level. That's the mission critical layer, which is basically defined in a technical manner that we have to fulfill soft real time. So it's not that critical than the safety critical layer, which actually means the mission critical application has a high priority, but failure will not harm any human. So it's not that critical than the first one. And we have the low critical layer, which is definitely not very hard to implement because we do not have to comply to real-time requirements. So in the end, we have to talk about the so-called MCS or mixed criticality architecture. That means we have a combination of hard real-time, soft real-time, and other tasks which are not of high priority. And if we talk about MCS, we immediately have to talk about automated vehicles, about drones or other unmanned aerial vehicles. So those kind of elements are mixed criticality systems. And again, this imposes definitely a lot of work to us as engineers, because we have to bring different timing constraints to one platform. We have to deal with safety critical, mission criticality, low critical systems, and fulfill and work out an autonomous driving stack that works 24/7. In our last part, we discussed the motivation of autonomous driving stacks. We discussed the different layers of the full stack, which consists of the hardware layer, the off-board layer of the software on-board layer, and all the methods and tools that are required to implement the full stack in order to achieve a final product. We introduced the high-level architecture of an autonomous vehicle. We discussed the signal flow within the different building blocks, sense, plan, and act. And we introduced the three different layers in the control block, which are the strategic layer, the tactical layer, and the reactive layer. And finally, we discussed what are the differences between safety criticality, mission criticality, low criticality, and we worked out that autonomous vehicles are so-called mixed criticality systems. In the next part, we actually will introduce the Autoware autonomous driving stack. We will discuss the different abstraction layers. We will introduce Autoware AI and Autoware Auto. And of course, we will discuss the development process, which is required to develop functions within the Autoware stack. And I'd like to give a brief outlook. What about the commercial use of the Autoware stack? Discuss the architecture of the Autoware AD stack. We will have a closer look at the two projects, Autoware AI and Autoware Auto. So actually Autoware was started in 2015, so some 5 years ago, by Shinpei Kato from Nagoya University. And it was planned as an all-in-one open source software for autonomous driving technology. The Autoware Foundation itself was actually launched in 2018. And it's a non-profit organization which supports open source projects with the overall goal of enabling self-driving mobility. And as you can see here, there are a lot of partners that joined the Autoware Foundation over the last 2 years. So what about Autoware AI? Autoware AI was the first project, and it's solely based on ROS 1. And it's available under the Apache 2.0 license. So what are the blocks that are parts of Autoware AI? So we have the localization block, which is achieved by 3D maps. We have implemented SLAM algorithms, simultaneous localization and mapping algorithms, in combination with GNSS and IMU sensors, inertial measurement units. We have the detection block. That one uses cameras and lidars. We have a couple of sensor fusion algorithms and deep neural networks already implemented and ready to use. And the third block is the prediction and planning, so the path prediction and path planning part, which is based on probabilistic robotics and rule-based systems, and partly using neural networks as well. So what is the output of the Autoware vehicle? It's actually twist of velocity and angular velocity. So actually yaw rate. If we have a closer look at the abstraction layers, and before we focus what Autoware is able to provide, let's have the big picture as discussed in part 1 of our lecture. And let's start at the bottom of this image. So that's the hardware part, so all the gray blocks are hardware parts. You see we have all the sensors in there, the Lidar, camera, IMU, GNSS, Ethernet, CAN. We have many and multi-cores platforms. On top of it we can distinguish, so it's not always the case, but it could be a mixture of GPUs and FPGAs. So there are platforms around that support both technologies. And we have to the right ECUs, which are mainly used for the safety part, for the safety controller, for the monitoring devices. On top of the hardware, of course, there is the operating system, where we distinguish between real-time Linux and real-time operating systems. And we have the runtime layer on top of it, so the blue blocks, which of course support the robot operating system. We have PCL, CUDA, Caffe, and OpenCV. And the application layer, so all the application software, so the algorithms, the running code, those are the green blocks, which bring sensing, perception, decision-making and planning, and the control layer to life. And on top of it, we have the driver interface. And the black box, as it's drawn right here, is the self-driving unit, so the autonomous vehicle that actually consists of those kind of blocks which are in this black box. And the red box as part of the black box is what Autoware actually is able to provide. So if you are joining the Autoware Foundation, if you're using Autoware, if you're installing Autoware in one of your vehicles, you actually will have access to certain implementations of sensing, perception, decision-making, planning, parts of the low-level control, and the driver interface. So let's have a different view on the Autoware AI architecture. So again, we have our main blocks that are supported by Autoware AI. That's the sensing block, the perception and situation awareness block, the localization block, the navigation block, the external part, so the maps that you have to create outside of Autoware go in there as well. And at the bottom, the actuation part, that actually means the path following, and depending on the vehicle, the PIDs. So that's what you actually get if you install Autoware AI. Once again, it's solely ROS1 based. And as we have discussed during our first part of the lecture, we also have safety critical topics that require hard real-time execution, and that actually gives us more or less the inspiration to work upon ROS1. And for that reason, Autoware Auto was launched. Autoware Auto is basically a re-implementation of Autoware AI, and the main difference now, it's ROS2 based instead of ROS1. We have clearly defined APIs and interfaces for different modules. That's also different to Autoware AI, so it supports more flexibility, more modularity, and you could easily exchange certain blocks. You have clearly defined APIs, exactly that what the automotive industry really likes and requires. And as an additional add-on, the state-of-the-art development process for software development has been set up, which is continuous integration and continuous deployment. That actually means that you are synchronizing your different software development parts on a regular basis, on a daily basis, or on a weekly basis. You have certain sprints. It's more or less focusing on agile development. A couple of years ago, it was originally in the automotive industry introduced and called seamless integration or model-based systems engineering. Those are still the names that are in common in the automotive industry. Now, with, let's say, more and more software in cars and mainly driven by autonomous vehicles, the software development process continuous integration and continuous deployment more and more takes over in the automotive industry. And just looking at CI/CD, what's in there, we have pull request reviews, we have pull request builds, we have a comprehensive documentation, we have 100% code coverage, there is a style guide for coding, and it's managed by an open source community manager. And feel free to just check out this link that I'm providing right here. If you have a closer look at the Autoware Auto development process, which is based on CI/CD, the original first step, like always, is you need to discuss the ODD, the operational design domain. Where is your autonomous car going to drive? Under what influences, external influences? So what is limiting your behavior of your autonomous vehicle? And that's basically, if you talk about level 4 autonomy, you always have a certain ODD. Level 5, for instance, would actually mean that the ODD is not limited and not restricted to anything, which is far away from where we are right now. That's why level 4 is basically the way to proceed, and there we have to talk about ODDs. The ODD-based development process is shown right here. So usually you choose an ODD, then you define this ODD. That could be just driving on a highway, or just driving during the daytime, or only up to 100 miles per hour, for instance, to make it a bit more fancy also for racing applications. So you have the definition of the ODD, then you have to specify different scenarios required to support the ODD, and that of course depends if you're in an urban area or if you're on a highway or somewhere else. And the feedback, or the closed loop, actually is that you, given the specified scenarios, are feeding back this information to choose the next ODD. Right now, so as the first Autoware Auto project, we have the autonomous valet parking AVP use case. That's our first ODD, and currently there are a couple of others in discussion, which could be the autonomous cargo delivery on closed private roads, could be the highway ACC, adaptive cruise control and driver assistance, could be the autonomous bus rapid transit, dedicated to fenced off lanes, or a fourth idea would actually be active campus navigation. So that could be the next ODD. And if we look once again to our picture at the top of the slide, if we choose the next ODD, we again go into our feedback loop, and when we specify the scenarios, we actually then start from the Autoware Foundation to develop support for the new ODD in Autoware. So that's actually the process, and this development support for the ODD is a continuous part. So actually here we have this continuous integration of new ODDs in our Autoware framework. Autoware is an open source project, both Autoware AI and Autoware Auto. And of course, we are interested in bringing Autoware to the market, that means to the commercial use. And there is one well-known company, Apex AI, that is currently working pretty hard to achieve that. You might recall the full stack that we have introduced in the first part of our lecture. So we have again the hardware stack, the onboard software, the infrastructure, and the final product. We have the Autoware AI project based on ROS 1. We have the Autoware Auto project based on ROS 2, with the first couple of ODDs and use cases coming up this year. And Apex AI builds upon that. Apex AI has two products, Apex OS, the Apex operating system, and Apex Autonomy. And this additional add-on to Autoware Auto actually is a huge improvement from ROS 2 from the Autoware Auto project, because right now, or what is Apex OS supporting, it's actually supporting a very high code quality, a production-ready code quality. It supports hard real-time, which is required for safety-critical applications. We have a real-time logger. It ensures system safety and system security. And of course, that's not that different to Autoware Auto. It's a complete documentation. But the main topic, of course, is that we, with Apex OS, it really will happen that the software stack gets type approved and can be used in, let's say, market-ready vehicles. Last part, we introduced the Autoware autonomous driving stack. We actually discussed the history of Autoware. We introduced the Autoware Foundation, and we discussed the two different projects, Autoware AI, which is ROS 1 based, and Autoware Auto, which is ROS 2 based. We also talked about the development process behind, which is based on continuous integration and continuous deployment, CI/CD. We discussed what operational design domain is currently supported by Autoware, which is actually the autonomous valet parking use case. And we also discussed what are possible next ODDs, so use cases that will be supported by Autoware. In the last part, we will discuss what kind of other autonomous driving stacks are around, and we will briefly introduce NVIDIA's DriveWorks and the Apollo stack. In this part, we will briefly introduce two different autonomous driving stacks. That will be NVIDIA's DriveWorks and the Apollo software stack. In addition, there is also the Electrobit Rubinos and Electrobit Rubinos predictor from this Finnish company called Electrobit, and all later parts given by Markus will solely focus on Autoware. So first of all, thanks to NVIDIA for giving us the opportunity to share the following slides. NVIDIA, and that's the main difference to Autoware, is not an open source autonomous driving stack. It's a commercial one. And if you look to the software parts, that's on the right, the NVIDIA software stack consists of several blocks, actually of 4 blocks. That's the Drive AV, the Drive iX, the DriveWorks, and the Drive OS. Within the Drive AV, we have the planning, the mapping, and the perception. Within Drive iX, there is the visualization, there is the AI copilot, and the AI assistant. DriveWorks itself supports the Drive networks with a couple of different subroutines, and the Drive calibration basically focuses on the link to the vehicle, where we have the ego motion, single track model is implemented there, the self-calibration, and a couple of different calibration tools. The Drive core, which is the bottom layer of DriveWorks, actually has the import and the input from the different sensors, the vehicle I/O, the image processing, so low-level processing, the point cloud processing, the deep neural network framework, and again a couple of different tools to be used. And the lowest level, of course, is the Drive operating system. And looking at the hardware, NVIDIA is supporting a couple of different hardware platforms. Pegasus is the one which is currently the best one that can be used for autonomous driving. and or also called the drive AGX. And for the entire vehicle, so with all the sensor kit, all the hardware to be installed, NVIDIA is actually selling a so-called Drive Hyperion developer kit. The platform to the left is actually the Pegasus platform that can be purchased right now. More information could actually be found. Just click that link, this hyperlink that I'm providing here. If we have a closer look to NVIDIA's product Drive Constellation, looking at the architecture, you usually have two different worlds, the software world and the hardware world. Software world actually is the simulation world, so it's not software like many of us might understand, software running in a platform. It's really the simulation, so the development, pre-development of function. So you have this so-called Drive Constellation simulator, which supports model in the loop and software in the loop, where you have its own operating system, the drive simulator, and the API to all the different sensor models, scenario models, vehicle models, traffic models, and the environment model. So we are just talking about models. Some of them might be capable of running in real time. Some of them are far away from real time. So that's the simulation part for function design, for optimizing a certain functional behavior. So it's usually in the automotive V cycle, in the left branch of this V cycle. If you look to the right, we have the Drive Constellation vehicle, which consists again of the operating system, of, let's say, exactly what we have introduced in the slide before, the drive core, the drive networks, the drive AV block, and the drive IX block. And the drive AV is actually pretty much comparable what Autoware is offering, perception part, mapping part, and planning part. If you're cooperating with NVIDIA, or if you're working with NVIDIA, you will see they are providing a lot of functions, algorithms in order to fulfill perception, mapping, and planning. Another software stack that exists is Apollo. Apollo is a software stack that has been launched in 2017 and stepwisely improved over the years. The next big plan will be next year in 2021, the ODD highway and urban road full autonomy. It's worth mentioning that in certain places in Japan, Apollo-driven autonomous vehicles are allowed to drive on public roads. The number of partners or supporters of Apollo is pretty big. Meanwhile, you can see here the current status, what companies and what institutions are part of the Apollo ecosystem. If we have a closer look at the software modules Apollo is offering, we actually see that we have data pipeline, the perception planning and control part, the prediction part, the map engine, and again a simulation environment. So not very different to Autoware or NVIDIA's DriveWorks. Apollo 5.0, the newest one, actually supports those 4 layers. If you start from the bottom, you see there is the Open Vehicle Certification Platform. Then there comes the hardware development platform, where we have all the sensors, all the units, control units that are needed, the GPS module, the IMU module. On top of it, you have the open software platform, including the algorithms for localization, perception, prediction, planning, the low-level control, HMI, and in addition, Apollo also offers a cloud service platform, which again supports security topics, over-the-air updates, V2X, And you also have the opportunity to map, so HD mapping part, the simulation part, and it's more or less the backbone is the data pipeline. Two additional autonomous driving stacks, the one provided by NVIDIA, so NVIDIA DriveWorks, and the one that is created by Apollo, the Apollo 5.0 stack. In the next session, Markus will take over, and Markus will give you, let's say, an introduction how to integrate Autoware in a real vehicle. The platform that Markus is going to use will be the Ford Fusion platform, and he will step by step introduce how to integrate certain functions of Autoware and Autoware itself to such a vehicle.
Hello everybody, also welcome from my side. My name is Markus and I'd like to show you the next two parts of this lecture. The first part is the integration of the Autoware AI stack into one of our research vehicles. I'm going to show you the requirements to get Autoware running. I'm talking about our vehicle and which software components are required to get it automated driving. Finally, I'm showing you a little bit about the mapping process for Autoware AI. The Autoware online class is in general about Autoware Auto, but in this lecture we are talking more about its predecessor Autoware AI, which was RON-based. But nevertheless, Autoware AI provides a huge selection of different algorithms, especially for planning and perception. A lot of different algorithms are available. You're going to find implementations for mission planning, motion planning, trajectory tracking, and also for camera and lidar-based perception, object tracking. There are a lot of implementations available, and you can have a look on GitLab. You're going to find a lot of useful solutions. Also, there are many simulation environments available which supports Autoware AI out of the box. And also the system is used since many years. So if you have any kind of issues, there is a large community which can help. But the development process continues, and also Autoware AI is going to have an end of life in the year 2022. In the next versions 1.15 and 1.16, only minor updates are going to be released. The main development is shifted to Autoware Auto, so don't expect any big changes or feature updates. In the next lecture, Yoshi is going to talk more about the differences between Autoware Auto and Autoware AI. So have a look at this lecture to get more details about this. What do you need to get Autoware running? This depends strongly what you're doing with Autoware or what you want to do. So when you would like to run the whole stack with Lidar localization, Lidar object detection, camera-based detection, then fusing of this information, planning, then you need a quite strong computer. So the recommendation is like 8 CPU cores and strong NVIDIA GPU, like 32 GB of RAM. But when you only do some planning and you're using the integrated Autoware simulator, then you're also able to run a quite simple version, and this runs also in a virtual machine. There are two possibilities to install the system on your computer. So one is you can make a Git clone of the repository or of all the repositories, and you can build it on your machine locally. And another version is that you use a Docker. This is also recommended from the Autoware community. So just pull the Docker and let's run the system. You can find a detailed explanation on GitLab. So just follow the link and have a look how to install it if you would like to use Autoware AI and try out some algorithms. Now I'm going more into detail about the integration of the Autoware stack on our Ford Fusion. In the beginning of 2019, we decided to install Autoware on one of our research vehicles. And as a target, we defined driving on our campus, where also our company is located, from point A to point B. So in the beginning, we did an evaluation which kinds of components are required. So like Daniel mentioned, you need object perception, object detection, you need the localization, you need the planning, you need a vehicle interface. So we looked into Autoware, which components are there available, how can we use them. So in the beginning, we started with updating of our demonstrator of our vehicle. So we upgraded the computing platform, and in parallel we installed the simulation environment to try out the things in simulation. The next step was then to look, okay, how is the vehicle interface? So in our case, we have from data speed an interface, so we can control the vehicle via CAN, we can throttle, brake, steer, and also we get vehicle data like what are the accelerations, the yaw rate, velocity, wheel speeds, and so on. The next step was then the Lidar mapping. So we created the point cloud of the whole campus, which was then in the next step used for the localization. And the Lidar was also mainly used for the object detection. To be able to drive automated, you also need an HD map. So therefore we mapped our campus. We created the vector map with the center lines, road boundaries, so that the planner is able to plan on the campus. We tried out different planners like the open planner and lane planner. On the right side you can see our vehicle, and below there is a picture then how our vehicle is finally driving on the campus, and also how the vehicle is detecting obstacles and considering this in the planning. And in the next slides, I'm going more into detail about the different required blocks. Here you can see some pictures of our vehicle. It's a normal off-the-shelf vehicle, a Ford Fusion. The only modification is the interface, so that we're able to brake, throttle, and steer. This interface is provided by DataSpeed. What you can also see on the left picture is the Lidar on the top of the car. It's an Auster with 64 layers. The Lidar is mainly used for the object detection, localization, and for the mapping. On the right side, on the picture on the top, you can see our main computing platform. It's a normal x86 computer. Then we have an automotive computing platform from TT Tech. We have integrated as a reference system an RTK GPS system with an high precision IMU. Then we have network components. And on the picture below, you can see some components from the power distribution and interfaces to the vehicle. This is the current hardware overview about our components. On the left side in the blue boxes, you can see the components, the sensors and actuators. Currently, we have integrated two front-facing cameras, full HD cameras, which are connected via Ethernet, and they provide a normal image. Then we have three lidars from Auster with 90 degrees field of view and 360 degrees rotating. With two sensors on the vehicle roof on the left and on the right side, we are able to see also obstacles in the near field of view, which are not visible for the LiDAR on the top of the car, on the rooftop. And one LiDAR with 90 degrees is also mounted in the radiator grille. So we can also see there are obstacles which are in the blind spot from the LiDAR of the rooftop. On the rooftop, there are also two GPS antennas. With these antennas and the RTK GPS system, we are able to localize the vehicle in a range of less than 5 centimeters when we get correction data via mobile. To control the vehicle, we have the ADAS kit from DataSpeed, so we can throttle, steer, brake, and we also get vehicle data via CAN. In the front of the car, additionally to the LiDAR, we also have a radar sensor. The radar is quite useful when you drive on the motorway. And we also have a third camera for mobile eye, but this camera doesn't provide images. This camera provides already object data. So what we are getting are where are cars, where are pedestrians, where are lane markings and traffic signs. So the last three components are connected via CAN, and all other components in the vehicle are connected via Ethernet. Now let's come to the more interesting part, to the required software components to get the vehicle running. So, like before mentioned, you need different components. Starting from the map, then you need your localization and object detection, path planning, where the path planning has different segments or different levers. What you need is to have a global planning, then a local planning, and then a trajectory tracking. So the local planner provides to the vehicle a trajectory. And about all these components, I'm going to go more into details on the next slides. So this is more or less like the overview about the required components. Let's start with the localization. So when you look how the most automated driving vehicles are driving, they are mainly relying on maps, on high definition maps. And to be able to drive together with a high definition map, you also need to be well localized in this map. And therefore, some possibilities are available to localize the vehicle. As an example, one is GPS. But GPS also has some drawbacks. So it's not every time accurate. You need additional correction data to really localize the vehicle in a centimeter range. But also when you don't have a very good field of view to the sky, as an example, there are skyscrapers or buildings, or you're driving in a tunnel, then you're not quite accurate localized. And therefore, Autoware provides a different approach for the localization based on a LiDAR sensor. And the most used in Autoware is the NDT matching node. So NDT stands for normal distribution transform, and it's more or less working. So you need a point cloud, which is created offline. So what you can here see on the left picture, there are a lot of gray dots in the background, and this is the point cloud created offline before. And then the NDT looks based on the live measurements. Where is my measured point cloud now in the offline recorded point cloud? And the output is then more or less the position of the vehicle in this point cloud. It's quite computing intensive to find your position inside the global point cloud when you use all your LiDAR measurements. So like when you have a LiDAR with 64 layers and it measures 2000 times per one rotation, so you wouldn't find a solution quite fast. So what you need to do is you need to filter your point cloud. So therefore in Autoware there is the voxel filter implemented, And with this, you can filter your point cloud. So on the right picture, you can see here less points. So the thick points are then used for the localization. More about the Lidar-based localization, you're going to hear in lecture 10, state estimation for localization. And you can find the Autoware.auto implementation on the following link. And also you can find the NDT implementation at the Autoware AI repositories. To avoid any kind of collisions, an object detection and tracking is required for the planning afterwards. Autoware has a lot of implementations for LiDAR and camera-based object detection. Here I would like to show you the LiDAR-based implementation. So what you can here see at the first picture are the raw sensor data from the LiDAR. The color shows the reflectivity, and this data is used in the first step to do a segmentation between ground and no ground. So therefore the ray ground filter looks, okay, what could be the ground and what not, and the ground is here blue visualized and afterwards not used. So only the red dots are used, and these dots are then used for the clustering. So the clustering algorithm looks, okay, which points are a cluster, and here in the visualization you can see then with different colors different clusters. And then finally these clusters are used for the object tracking. In Autoware AI there are different implementations for the tracking. If you're more interested, you can look on GitLab in the repository core perception. And also in Autoware Auto there are already some algorithms implemented, so you can already find the ray ground filter, which gives you the ground and no ground, then the point cloud clustering and object tracking. You're going to hear more about this topic in lecture number 7, object perception with a LiDAR. The next topic is the planning, and the planning has more levels of hierarchy. So it starts with the route planning. The route planning is like the mission. So the vehicle should go from A to B, and the output of the route planning is then which roads needs to be considered to go there. So when I would like to drive from Vienna to Berlin, I would get like the motorways and all the kind of junctions. And in Autoware, it's the global planner. And then the next level is the motion planning. So the motion planning has as an input the path of the route planning, and the motion planning then considers all kinds of obstacles, speed limits, zebra crossing, traffic lights. So all the things which are at the planning moment relevant. There are different implementations in Autoware. So there's the open planner, then the lane planner, and as an example, the A-star. So different algorithms you can find on the GitLab at core planning. Here's an example. You see the open planner. So in the front of the vehicle, there are multiple trajectories which the vehicle can use, but when they are red, then they are blocked. And in this case here, we have a vehicle which is leaving a parking space, and that's the reason why all the trajectories are blocked. And then the final selected trajectory also needs to followed by the vehicle. And therefore the motion controller is used. And in Autoware there are different implementations. So you can use a Pro Pursuit controller or an MPC. And also in Autoware Auto there are already different implementations available. So at following links you can find more information. And in lecture number 13, motion planning and control, you're going to hear much more about this topic. The last part of the integration process, which I would like to show to you, is the mapping. We use the mapping for two things. One for the localization, like said before, for the Lidar-based localization. Therefore, we mapped our campus with a Lidar with 64 layers. And we use the entity mapping algorithm, and the output of the algorithm is a point cloud, which you can see here on the right side. The second part of the mapping process is then a creation of a HD map. So which lines are allowed to drive, what is the speed limit, where are traffic lights, zebra crossings, and therefore Tier 4 is providing a browser-based tool, so you can upload your point cloud, and in the browser you can then draw your route network. And depending on the Autoware version, you can use Lanelet 2 or the vector map. And with following link, you can find the tool. So this was finally our last step of the integration of Autoware at our vehicle. I hope you have now a little bit of a feeling what's required from Autoware to get it running on a vehicle. And finally, I have a video how the vehicle is driving on our campus. So let's have a look. In this part of the lecture, I'm going to show to you different use cases for Autoware. The first one is why we are using Autoware at virtual vehicle research. The second one is how I'm using Autoware as a base layer for my PhD thesis. And the third one is how we are using parts at our autonomous racing Graz team. Like Daniel mentioned in the beginning, automated driving isn't really an easy task. You need to have a lot of building blocks to get the whole system running. You need to have all the sensor interfaces, the vehicle interface, perception, localization, high-level planning, low-level control. But also you need a lot of other tiny components like a camera lidar calibration, system monitoring, fault detection if you have any kind of issues with one of the component. And Autoware provides a lot of components to handle all these big or small issues to get the vehicle running. Therefore, we decided last year to deploy Autoware to one of our 3 research vehicles. Also for us at Virtual Vehicle Research, it's not that easy to develop a whole autonomous driving stack because our main focus is more applied research. Therefore, we work together with different car manufacturers, suppliers, research institutes, and with other universities. And there our focus is not to develop a vehicle which is able to drive in any kind of situations autonomous. We are more focusing on specific topics in the development phase of a vehicle. But when you would like to show as an example a camera-based perception and which influence this have to the planning, you still need to have the whole automated driving stack running to see any kind of effects. Another important thing for us is that a lot of simulation environments provide an interface to Autoware. So you can use Gazebo, the LG SVL, or the Carla simulator to try out things. So you don't need a real vehicle to get it running in the beginning. And also, I'm sure the most don't have a car to try out things. So with the simulation, you can try out many things. And also what's quite important, all these simulators are open, so you can look inside. And also there's a big community which can help you with any kind of issues. And also in one of the next lectures, there's going to be a detailed presentation about the LG SVL simulator. So let's see what the guys talking about their simulation environment in the future. In our case, we are also working strong together with the university. So a lot of students writing their master thesis or bachelor thesis at our company. And then it's quite useful when you have an environment for the students which they can use immediately. You can find a lot of videos on YouTube about how you get things running in Autoware. And also what's quite important, you find a lot of papers where the implementations, the algorithms are well explained. And also, when a student has finished his work, he can also then show afterwards the community some results. On this slide, you can see some pictures from work from us where we are using Autoware. So we are using Autoware, or we are using different parts of Autoware. So we are using the Lidar-based perception, camera-based perception, Lidar localization. And also what's quite important for us is, like our vehicle has an interface from DataSpeed, and they provide for the vehicle a gazebo model of the car. So we have exactly the same interfaces in gazebo than to the wheel car. So this makes it quite easy to do integration tests. So when Autoware works together with gazebo in the simulation, then I'm also quite confident that the functionality is running on the car from an integration point of view. Of course, like you can't do all kind of LiDAR tests or camera tests. That's not working perfectly, but you get a feeling if a function is running or not. One student of us, Thomas, he's doing quite a lot with occupancy grids and the LiDAR. So he is investigating how many LiDARs do you need to drive in unstructured environment. So it's like one LiDAR enough when you also create a map during the driving. And also what we're trying out is like the planning implementations like the open planner, the lane planner, hybrid A-star. So there are a lot of useful components which we are using as a base layer for our driving functionality. The next use case I'm going to show to you is my PhD thesis. The thesis is more or less about critical situations with pedestrians when you have an automated driving vehicle. The collision avoidance system is able to handle critical situation like there is a person jumping out behind the parked car, or there's a failure in the object prediction, and then the motion planning isn't able to react because like the pedestrian was detected by the system too late. And in situations like this, you need to react quite fast because especially with higher velocity, like every millisecond counts for the speed reduction. And therefore the collision avoidance system is running in the background and also observes the situation. And depending on the situation, it then triggers emergency braking maneuver or an evasion maneuver. Like you can see here on the two pictures on the right side, there's a braking and an evasion maneuver. So what are the interfaces to the collision avoidance system? As an input, all the traffic participants around the ego vehicle are needed. So there are pedestrians, there are cars. Another important input is like the HD map. So the function needs to know where is the driving lane for the ego vehicle, where is the oncoming lane, where are the road boundaries, to to interpret the situation much more in detail. And also, like, the system is running in the background and the vehicle is driving. So the automated driving functionality is able to provide to the collision avoidance system a trajectory. So the system already knows in advance where is the car in the next, let's say, 2 seconds, and can then predict or calculate the criticality of the situation much better. And as an output, then the collision avoidance system provides a modified trajectory depending if there is a braking or an evasion maneuver. In the beginning, I started the implementation of my system mainly in ROS. So the vehicle was modeled in ROS and also a simulation environment. But when you go to the end and you would like to bring the whole functionality into the vehicle, then you need to have a complete vehicle running in autonomous mode. So therefore, I decided to use Autoware as a base layer. So which kind of components did I use? Mainly 3. So the first one is the mapping. The mapping was one side used for the Lidar localization, and then on the other side for the HD map. So to draw on the proving ground and on our campus where is the vehicle allowed to drive and where are the boundaries and these kind of things. The second big block is then the localization. So the Lidar localization was used, and what's also necessary when you do a low level control with, let's say, strong maneuvers with high accelerations, also the planner needs to get the position with a high update rate, and therefore Autoware provides an extended Kalman filter localizer, which has as an input both of the Lidar localization and the vehicle odometry, and then you get, as an example, the position of the eco vehicle with 100 Hz. And for the automated driving functionality, 2 blocks were used. So one like the global planner, which delivers you the trajectory to go from point A to point B. And this is then used for the motion planning. So there were, depending on the use case situations, 2 types used, the lane planner and the open planner. On this slide, you can see the architecture of the system. On the left side, there are the interfaces to the sensors and actuators. So in our case, we are able to access all the data via ROS on the vehicle. So it's quite easy to interact with the car to get all the data. And on the right side, there is the software stack simplified visualized. So we have different components. One important component is the Autoware stack, which is in charge for the localization, then for providing the map information and the reference trajectory, which is one of the input for the collision avoidance system. The collision avoidance system also gets data from the vehicle, and of course also the system needs obstacles around the car. In our case, we have 2 collision avoidance systems running in parallel. So one has a little bit of a reduced functionality. It's only able to perform braking maneuvers, and also it can handle situations where not that much information are provided from the automated driving stack. So as an example, there is no lane provided or information from a map. Also, this is like of a fallback solution. So the collision avoidance systems are getting the reference trajectory from Autoware, and if there is any kind of critical situation, then this trajectory is modified, and then the trajectory selector forwards this trajectory then to the trajectory tracking, which is then used for the low level control. After deploying the collision avoidance system to the vehicle, the next important thing in my thesis was then the validation. Therefore, I had the chance to validate the functionality on a proving ground. The proving ground was provided by AVL, a company located in Graz, Austria. And what you can see in the picture above is the proving ground mapped. So the gray dots are the point cloud. And you can also see the vehicle driving on the proving ground, and the white thick dots are the measurements from the Lidar. Above here, you can see now what the system sees. So in the middle, there's the camera from our vehicle, and there's a virtual overlay. So this is just like a screenshot from Arvis. And what you also can see in this picture here are like these small blue dots. This is the Lidar measurement, that's the ground. Then we have all the Lidar measurements above the ground, they are red. And we can also see the trajectory of the ego vehicle, here colored, and also from the pedestrian, an area where the pedestrian could be. So in our case, we are using a reachability analysis to predict where a pedestrian could be in a worst case. And the color corresponds to the time where the pedestrian or the vehicle is. And also one nice thing is like the image above, it's from a standard Arvis plugin, it's called Camera. To get this, you only need the camera image, then the camera info, and you need the extrinsic of the camera. So you need to know where is the camera placed in relation to the other sensors in the vehicle, and then you get immediately an overlay. On this slide, you can see some results from the validation. The collision avoidance system has two functionalities, the emergency braking and the emergency evasion. And here on the left, you can see a scenario where the ego vehicle brakes and 3 different time steps are visualized. So in the top, you can see the ego vehicle. The maneuver started with about 60 kilometers per hour. And at this time step, the pedestrian is already on the driving lane, and the ego vehicle performs an emergency braking maneuver. So it decelerates with minus 10 meters per second square. The second image, it's the same. The ego vehicle decelerates. And in the third picture, the ego vehicle stopped and the pedestrian passed the driving lane safely. On the right side, there's the same, but in this case, the pedestrian or the collision was avoided by an evasion maneuver. So in the top, you can see the pedestrian crosses the road, and the colored circles are the place where the pedestrian could be at a defined time. This is provided by the reachability analysis. And below you can see the ego vehicle passing the pedestrian. And the trajectory of the ego vehicle is a jerk optimized, so it's also quite comfortable to drive. And also during the tests, it felt quite smooth during the situation. And in the end, you can see the ego vehicle passed the pedestrian with a complete lane change to avoid the critical situation. My colleague Wolfgang made a video about the testing on the proving ground. And what we used for the evaluation was a crash test dummy. So you can drive against it and it doesn't damage the vehicle. Also, you can reproduce every scenario exactly, which is quite important for the validation. So in the beginning, we mapped the proving ground of AVL. You can see here the point cloud and the localization of the vehicle using Autoware. And in the first step, we evaluated the braking functionality. So we tested the functionality up to 60 kilometers per hour with a full emergency brake maneuver. And the same we also did for the evasion. And some parts of the implementation and validation happened in that project Autodrive. And also I would like to say at this big thanks to the Autoware community for providing their base layer. Without the base layer, I'm sure I wouldn't be able to drive that fast with my functionality in a real vehicle. So thanks a lot. Now let's come to our final use case. It's about autonomous racing, and that's also my favorite use case. Last year we established a racing team. It's called Autonomous Racing Graz, and we are part of Race. Our team members are from Graz University of Technology and from Virtual Vehicle Research. So we're like a mixed team. And so far we participated at 2 events. Our first one was last year in September. It was a localization challenge. And the goal there was to drive on a track with a lot of gates. And the gates had a width of the vehicle width plus like half a meter. And there was no GPS provided for driving. So the challenge was to get the localization done with a Lidar. And we achieved the second place. We were quite happy because we had a quite short preparation time of about 7 weeks. The second challenge was then in France. It was on a real racetrack, similar setting, but with higher velocities and less space between the gaps. It was only 30 centimeters more than the vehicle width. And there we achieved our first victory, and also we achieved the fastest lap time. I'm going to show you now 2 videos that you get an impression about what's going on there. The left one is from Hungary, from the localization challenge, and the second one then from the event in France.
Robo-race.
Let's go now a little bit more into details. We decided last year to use parts of Autoware because like the biggest challenge was to do the localization without GPS. And we had already a lot of experience with the NDT implementation from Autoware. So we decided to use this one for the localization. Before we tried it out on urban driving and also on the motorway with a little bit higher velocities. And also it showed that the algorithm is quite reliable and robust. So then it was quite easy to choose the NDT implementation. So why did we use it? We used it in the first case for the localization and also in the second case for the mapping of a racetrack, because it's also quite important that you know where are road borders so that you can calculate the optimal racing line. And the good thing is when you do a mapping and you have a 3D point cloud, you can see quite well where are curbs, where are borders of the racetrack. So you can then afterwards draw your borders of the race line with some tooling. And then you can afterwards use these borders to generate an optimal racing line, which you can see here on the picture, so that the black line is then the optimal racing line, which is then used at the race car. To calculate the optimal racing line, we used a tool from the Technical University of Munich. They have a well implementation, and it's also on GitHub. So when you want to use it, just Google. You're going to find a quite well solution. What did we need to do to map the racetrack? So in our case, we had the Lidar with 64 layers from Autoware, and the Lidar provides a point cloud, and this point cloud is then used at the NDT mapping node, and then the output is a point cloud. So this is all done offline. We record once with a normal car or with the race car a lap, and then offline the point cloud is created. On one side we had the mapping of the racetrack, and then on the other side we have the LiDAR-based localization. So on this slide you can see an overview about our architecture, which was used or is used for the localization. So what you need is you need to have a map. Therefore we need the map loader from Autoware. Then of course you also need the algorithm which is doing the localization. So there we are using the NDT matching algorithm. And as an input, the node has also some data from the race car. So we get like velocity, accelerations, the yaw rate. And you also need, of course, the LiDAR measurement. So this is the third input, but you can't use the whole raw measurements from the LiDAR. You need to reduce the amount of data. And therefore the points downsampler is used, and it's a voxel filter. So it's a 3-dimensional reduction of measurements to get the thing running and to get a localization in a defined time. Then there's also one block called LiDAR distortion. About this I'm going to talk in the next slide. It's more or less correcting the measurements from the LiDAR based on how the vehicle drives. And we have the interface to the LiDAR. So in our case, we use from Autoware a LiDAR, a 16 layers LiDAR at the race car for the localization. And they provide a ROS node to get the data from the sensor. And then we also have an interface to the vehicle where we are sending the output of the NDT algorithm to other software components of the car. This is now a little bit of an off topic. It's not really related to Autoware, but I also would say it's quite interesting when you work a lot with LiDARs, and especially when you're doing localization and also object detection at high velocities. When you look on a LiDAR sensor, which measures 360 degrees, the sensors are rotating. And this means they start at a defined point where they start the measurement, and when they have finished one round, they stop the measurement, and afterwards you get the point cloud, and for every point you also get the timestamp. So you know exactly at which time the point was measured. This means when you're standing still with your vehicle, this doesn't have any effects, because all the measurements are from a stationary point. But when your ego vehicle is moving, also of course your sensor is moving, and you're doing a measurement, but during the measurement you are moving. So like the Lidar point cloud gets a distortion. And what you need to do is, when you would like to have a quite good localization, you need to do a correction of this distortion. So how does the distortion look like on a real measurement? So on this picture, you can see here in the middle, there's our ego vehicle, the DevBot. And what we have here as an example is we have a parked car. So the parked car was also here during the mapping process. So the location of this car is well known in the point cloud. And our LiDAR sensor starts the measurement clockwise and backwards. So it starts like here, and it goes into this direction. And the blue lines are the measurements from the LiDAR. So like you can here see, the measurement is a little bit in front of the car. And this is based on the circumstance that the ego vehicle is now already on a different position compared to the point where the measurement was. So the distance was correct measured, but only for this timestamp where the measurement was done by the sensor. And what we did at Rover is we did a correction of the measurements. So all points were corrected based on the current velocity of the DevBot and also based on the yaw rate. And what you can then see here is, like, in the beginning, there's a big gap between the measurement and between the distortion. And in the end, the error is going to be 0. One colleague, Tobias, wrote a nice paper about how the distortion works and how we used it at Rover. So if you're interested in this, have a look on his paper. Now I'm going to show you some results from the localization performance from the event in Salason in Hungary. There we had the possibility also to log the GPS data from the car during a training session. So what you can here see in this diagram is the error between the LiDAR localization and the high precision GPS system. What you can see here quite well is the error is more or less every time below 20 centimeter. Sometimes there are peaks where there's an error in the localization. But nevertheless, when you look on the histogram, you can see quite well that in the most time, the NDT delivers a quite good result. And what you also need to consider, this is only the LiDAR localization. And so there is no filtering together with the vehicle autometry. Together with this, you're getting a much lower error in the position. But still, this is like an evaluation of the CPU load during a race on one of the computing platforms in the vehicle. And what you can see here is the CPU load. So in general, it looks quite good, but you can also see that 1-2 cross have sometimes a quite high load, so there are a lot of peaks. And this is more or less on the, let's say on the issue that when you drive quite fast and you have like changes in the orientation, the NDT algorithm needs more time to find the solution. But nevertheless, we tried out to run it only on the CPU because we didn't want to use the GPU. And also we were able to localize the DevBot at every time on the racetrack. And also we figured out that the implementation is very stable. So from our side, we are quite happy with the implementation, and it showed it works at high accelerations and also with high velocities. Finally, I'm showing you a short video about the localization, how it worked in Hungary at the localization event. What you can see here on the picture is the DevBot driving. The colored lines are the measurements from the Lidar, and these small gray white points, these are the points from the point cloud used for the localization. What you also can see quite well, there are not a lot of features, there are only some cones and barriers, but nevertheless the DevBot is able to localize. You can also here see some trajectories. These are like differences between different labs. And finally, the DevBot drives again back to the garage. If you're more interested about our racing team, we have a website. It's called autonomousracing.ai. Have a look on it. Also, you can follow us on LinkedIn or on Instagram. So this was the final use case for Autoware. I would like to say thank to you. I hope you get some motivation why it makes sense to use the whole stack or maybe some parts of Autoware for your projects. Thanks a lot for listening of this Autoware lecture. We hope you learned a lot about autonomous driving stacks and how we are using Autoware in general. And I would also like to say a big thanks from the Autonomous Racing Graz team to the Autoware community for the NDT algorithm. The implementation works quite well and also at high velocities, so great, thanks a lot. In the next lecture, Yoshi is going to talk about Autoware in more detail. He's going to talk about the different implementations and how you can use it. So stay tuned.